We've seen now how we can deal with objects that exist in one dimension, cut up their length, and then add up their length to get the total. And we've seen how we can do this in 2 dimensions, cutting up the length of our 2-dimensional object into a length in each dimension, adding and multiplying them to get an area, and then adding up all of the little areas to get a total. What happens if we go into 3 dimensions? So we want to look at some surfaces that we might encounter in 3 dimensions and what we can do, how we can use this idea of cutting up lengths into smaller bits and then adding up their bits to get surface areas. As usual, let's start with something simple. Let's suppose we have a rectangular prism and we wanted to know its surface area. So we're not talking about volume yet. We just want the surface area of this prism. Well, let's suppose that it has a length and a width and a height. Now you can sort of see what the pattern is going to be. We've got an area here that we want to know it, and we're going to have the same thing over here. So we call that A1, and this is the same A1. And we're going to have an area here and on this backside. And so if we called this, say, A2, that would also be A2. And then we've got an area on top. And we might call this A3, and on bottom you have the same thing. And so our total area, surface area, is going to be 2A1 plus 2A2 plus 2A3. But any given piece, it's just a matter of making sure you get your line segments correct. So if we looked at the front side, if we looked at this top side, for example, we might call this the x direction, the y direction, and the z direction. And so this little piece on top has a dx and a dy. If we went to the side, say we went to this side, it would have a dz and a dy. And if we went to this other side, we would have, in this case, a dx and a dz. And each of these would get an integral from 0 to L if it's dx, W if it's, or the width, the length if it's x, the width if it's dy, and the height if it's dz. And so it's fairly straightforward. We use the same techniques we've used before, and we just have to do it multiple times. As usual, this gets more interesting when we move to some geometry that isn't rectangular. So let's suppose we wanted the surface area of a cylinder, and again, this is surface area, not volume. Well, how would we compute that? We can do what we've done before. We can take this entire surface, which is this whole cylinder, and we can cut it up in bits. Right? For example, this top bit is a circle, and then on the bottom, this is also a circle. And so we can actually say, well, all right, there's a circle and a circle, and this barrel, I'm going to call it this bit. So let's call this the barrel. And so the area of my cylinder is just going to be equal to twice the circles plus the barrel. And we already know how to calculate the area of the circles, right? We can do what we've done before. We would have some arc length. This would define some arc. This might be a d theta. And this arc would have some thickness. This is usually considered, so anywhere radially out this direction, for example, this would be my R direction. So this would be some little piece here that has an arc length ds, and then this side would be dr, and so the little d area would be ds times dr, just as before, and just as before, ds is really r d theta, dr. And we would add up these, and that would give us the area of our circle, and we'd multiply that by 2, and that would give us the top and the bottom. So this one we already know, so I'm not going to do that one again. Instead, it gets a little more interesting. So what's the barrel? Well, let's look at this. This is still the same arc as before, so we still have this being a d theta, this being a ds, where ds is r d theta. But now instead of going in radially, we're going up. We want to go along this direction, and this again is the z direction. So we need a thickness. We need a piece that looks, something like that. We've got ds. What is the other side's length? Well, this is a dz. And so now our dA is going to be ds times dz, or in other words, r d theta dz. And since this system has the usual properties, this geometry, and we've chosen our geometry with the usual properties that, our theta is entirely independent of our z, we can just integrate this. And you might say, well, what about this r? What is that r? Well, it would be the radius of this cylinder. And so really this wouldn't be just r d theta, this would be radius d theta. And so we would have the integral from 0 to 2 pi r d theta times the integral from, say, 0 to my height dz, and I would integrate that. And so I would get 2 pi r times my height. And so 2 pi rh would give me the surface of this barrel, and I could add it to then the surface of the circles. And that would give me the total surface. So this would be the area of the barrel. Now you might call that hard mode, and we could do easy mode. Again, instead of doing an integral in theta, we can sort of pre-do our integral, given that we know that this is going to be a set of rings, and the rings all have a length of 2 pi times r. And so that's my length in one direction, and in the other direction, my length, this would be my first length, my second length is still dz, and so I could also do my area, simplify it out to be 2 pi times my radius dz, and then integrate this. and I would get the same thing. I would go ahead and get 2 pi r h as the area of my barrel. So however you want to do it, whether you want to do it easy mode or you want to have to go, and again, we can do this when the geometry lets us. If the geometry is nice and has no angular dependence, maybe that lets us do it this way. But maybe if it has some angular dependence in, say, if the distribution of charge, distribution of mass, or whatever it is we're trying to calculate, we might have to go back to hard mode again, where we have to calculate this little differential bit, but we know how to do that. And so we can use this idea to get a surface area of a cylinder. Now we're ready to tackle the last major type of geometry we might encounter, and that is spherical geometry. Now, the hard part for most students when dealing with spherical geometry is the fact is working out the different lengths, the different angles and circles that they've got to work with. So let me walk you through that. In spherical geometry, we're going to have 3 coordinates. We're going to have this radial coordinate, this angle that's coming down from the vertical direction. This is the zenith direction, and usually we call this the polar angle. And then we're going to have one that's moving around the plane of the circle, and this is called the azimuthal angle. And so we've got the radius, the polar angle, and the azimuthal angle. As far as notation goes, you might have learned this. These might be switched up. For example, you might have learned that the azimuthal angle as a theta and the polar angle as phi or phi. You might have learned the radius, for example, not as r but as rho. Honestly, there's a million different ways we could notations we could use. So I'm just going to use what I've got. I'm going to call my radial direction r, my azimuthal angle phi or phi, and my polar angle is going to be theta. Now, I've got to work out my lengths. Remember, we're always going to treat these areas as though they are some rectangle with 2 lengths that we're going to multiply. So I'm going to have a length 1 and a length 2. And really, you can already see, since we're on a sphere, these are going to be arc lengths. So in one direction, we're going to have an arc length that comes down from the pole, and we might call that a ds theta. And the other one, we're going to have an arc length that is sweeping around the plane of the circle. We might call that ds phi. To work out ds theta and ds phi, it helps to realize that one lies along a line of longitude and the other lies along a line of latitude. So this is a line of longitude, and this is a line of latitude. That's a DE. Latitude. And so in one case we have a big circle. Remember, if we think of lines of longitude, they run from the top of my circle all the way down to the bottom, and they are making one giant circle. So this side is at a constant radius of that is the same as the radius of the circle. We might say capital R, for example. Whereas my latitude line, it is going to depend on where I am on my circle, because it's, for example, near the poles, it's smaller, and then as I get near the equator, it makes a bigger circle, and the radius of this circle is a projection. It depends on how much this line projects down to some line here, okay? Because it's going to make now some circle that's like that big as it goes around. right? Obviously, that's a terrible drawing. But you can see how I'm going to have to work out. One is easy. It's just the same arc as we've worked out before. This is going to be, of course, r d, my angle, which in this case is theta. The other one is also going to be some length d, my angle, but this length, we've got to work out what that is. So let's look at that. Let me draw this from the side. And you can see what that angle is going to be, or what that length is going to be. Let's draw a circle. And if I come out from the radius upwards, and I want to project it down onto the plane of the circle, this plane here, right? This plane there. I've got to project it downwards. So I'm going to project it down this way. And I want to work out what this length is. Well, this angle is theta, and this length is r. So I've got the hypotenuse of a triangle and one interior angle. And so this length is r sine of theta. When I put this all together, then, for my arc lengths, I'm going to get a ds theta that is just r d theta, and a ds phi that is now r sine theta d phi. So my area, this little area element, is going to be r d theta times r sine theta d phi, or I might write this r squared sine theta d phi. Now the other tricky bit is the limits of my integrals, because both of these, both theta and phi, are on a circle, and so you might be tempted to say, well, I'm going to go d theta from 0 to 2 pi, and I'm going to go phi from 0 to 2 pi. But if you do that, we have a problem, because this side of my circle, for example, is going to be swept around this entire circle, and that's fine. That makes up, right? I take a hemisphere and I sweep it around a circle and I get a sphere. But I'm also going to sweep this back hemisphere through a full circle. And so I'm going to actually get two spheres. I'm going to cover every point on the sphere twice. So one of my angles, be it d theta or d phi, one of them can't be through the full circle. It actually has to be just a hemisphere. So honestly, it doesn't really matter which one. Usually, it's typically the polar angle. Sorry, that's not this one. The polar angle that gets the half circle, and the other one that gets the 2 pi. And I've seen this run from 0 to pi, or sometimes the limits might be minus pi over 2 to pi over 2. It really doesn't matter as long as I go through a half circle. And then the other one is going to go from 0 to 2 pi through the full circle. And when I do that, now I will get just one circle. I won't double count my points. Putting it all together now, we found that our area element is r squared sine theta d phi. Our total area is going to be the integral of all our little differential areas. We know that our r is now at the radius of this sphere. So we're going to have r squared, and we want to integrate sine of theta d theta. And we want to do that around half a circle, so that would be 0 to pi. And then we're going to integrate d phi, and we want to do that for the whole circle, so that's 0 to 2 pi. My integral from along phi is going to be easy. This is just the integral of dx, so it's just x evaluated at the endpoints. So this is just 2 pi. The integral of sine theta d theta, this is going to be minus cosine of theta evaluated at its endpoints. And then I've got an r squared here. So when I multiply all these together, I'm going to get my answer. Cosine of theta evaluated at 0. So I'm going to have the cosine minus the cosine of pi plus the cosine of 0. The cosine of pi is -1, so this whole thing together is just 1. And the cosine of 0 is 1, so 1 plus 1, this is 2. Putting it all together, I get that the area of my sphere is just going to be r squared times 2 pi, or as you might see it more naturally, 4 pi times the radius squared. And that is then the surface area of a sphere. You've seen now how we can apply this idea of integration, where we take something, we cut it up into little bits, and we add up all the little bits to finding now the surface area of something. You've seen it applied in Cartesian coordinates, in cylindrical coordinates, and in spherical coordinates. The only thing left to tackle now is going to be applying this not to a surface, not to a length, but now to a volume.